Hello and welcome to another edition of the Radio Mechanics 10-buck test bench. And because time is getting short and I'm planning a move to Thailand next October, things are going to get a little bit hectic here. I can live in Thailand I can rent in Thailand for what I'm paying for electricity here in New Hampshire. It's going to make a much better retirement, and I've got a lot of friends over there. I've accumulated about 3 years plus time in that country, and very familiar with it, comfortable with it, love the food, love the people, just like everything about it. So we got to get this out of the way, because hopefully by next October I'll have my house ready to rent, and that'll add a little bit to my Social Security and my 401k, and I should be able to live quite well over there. If I find the right location, we'll be able to move some of this gear over and continue from there, hopefully. At any rate, what do we have here? We have a newer precision sweep generator with the built-in marker adder. Now, I picked this up so that I wouldn't have to have an additional marker adder. We're going to hopefully get a chance to restore that RCA marker adder and use it with this sweep generator. It'll all depend on time. I'm going to concentrate on getting this one up and going so that we can continue the FM series. I have an FM receiver over here. I will probably restore this one instead of the one I showed in the previous video. Cosmetically, this is in pretty good shape. This is a Howard FM converter. And what this is when FM was becoming popular, most radios were AM. This unit received the FM band and had an output in the back to connect to your phono jack. Most AM radios of the day had a phonograph in them, and this would have had originally an RCA connector on the back to plug in to where the phonograph went, so you could have an AM and FM receiver. And this is a nicely built little unit. So we'll get into restoring that and go through the alignment on that using the new precision sweep generator with marker adder. What are the advantages of this one over this one? Well, again, it has the built-in marker adder. You don't necessarily have to have the marker adder. This will do markers as well, but this adds them after the demodulation of the signal, which means they are much cleaner and crisper on the oscilloscope screen, and we'll see that when the time comes. This old unit uses a mechanical sweep generator internally. It looks like the voice coil of a speaker with a disc that moves in and out and changes the capacitance and the inductance of a circuit to cause the signal to sweep back and forth at a 60 hertz rate. This unit has electronic sweep generation. They're both vacuum tube units, but this is a much newer version. This thing weighs 20 pounds, if you can believe it. This one only weighs 12, and it incorporates the marker adder internally. So we're going to jump on this first, get this up and working correctly, then we'll restore or recap the Howard, and then we can go through the FM alignment. Now, why do we need a sweep generator to do FM alignment, or for that fact, television alignment? It has to do with bandwidth. And let's put this thing up here. The reason there's more bandwidth is there's more allowable bandwidth on the FM dial, or the FM spectrum. And that was done because A, it's operating at a higher frequency. There is more bandwidth available. Therefore, as receivers became more sophisticated, speakers became more sophisticated, and people started crying for better fidelity, they allowed a wider bandwidth. Now, an AM signal is only allowed 5 kilohertz of audio bandwidth. That's not much better than a telephone. Your standard telephone, has a bandwidth, an audio bandwidth of about 31 or 3.1 kilohertz, or 3,100 hertz. Not very good. It's perfectly good for clear, intelligible speech, but certainly doesn't do a good job of music reproduction. People, excuse me, people think that the high fidelity comes from FM and AM is, you know, just can't have the fidelity. That's incorrect. The lack of fidelity on AM is the restriction of the bandwidth to 5 kilohertz of audio. This was done way back in the day when, first of all, it didn't matter much if you had a narrow audio bandwidth. There weren't speakers and amplifiers that were really capable of reproducing much better than that. And because they operated at a lower frequency range, around 500 to 1600 kilohertz, there wasn't a lot of spectral room in there. So they limited the bandwidth of the entire AM signal to 10 kilohertz spacing. So you've got 5 kilohertz of audio. You're going to have some side bands produced from that. So they made everything 10 kilohertz apart to try to get as many channels into the AM spectrum as they could. That's the reason for the low fidelity on AM. It's not that it's AM, it's just that it's artificially constricted to 5 kilohertz of audio bandwidth. If we had a wide open AM spectrum and you were allowed to run 15 or 20 kilohertz of audio bandwidth like you are on FM, which is on a much higher frequency spectrum, the fidelity would be virtually identical. Now, FM has the advantage, of course, of noise immunity to impulse noise, lightning noise, electrical motor generated noise. So that helps. Along with the additional bandwidth, you get a much cleaner signal. But if you were allowed to open up the bandwidth on the AM and you had a noise-free signal, it would be virtually identical to the FM reproduction. Okay, when you tune an AM radio, when you peak an AM radio doing alignment, you peak the IF transformers, basically just to a peak. Except in the case of some special shortwave receivers, this is the way it's always done. You set your signal generator to 455 kilohertz or whatever the IF happens to be of that particular set, and you merely peak it, and you're done, because the 3 dB points will fall within that 5 kilohertz allowable bandwidth. Now, FM signals being allowed 3 times as much bandwidth, 15 kilohertz, the 3 dB points have to at least encompass that 15 kilohertz bandwidth. So on some receivers, they stagger tune 2 IFs. Some receivers are designed to have multiple coils in, and they'll have a double hump. All depends on the manufacturer. But to do this correctly, you can't just peak it, because if you just peaked these IF cans or IF transformers like the AM is peaked, you wouldn't have any audio bandwidth. Your fidelity would be back to that of AM. You'd end up with a very narrow constricted signal. So you have to have this bandwidth, and to do that you have to have a signal generator that you set to the center but swings back and forth at this 15 kilohertz bandwidth, so that you can properly make sure, or ensure that when you tune these coils that you end up with the proper bandwidth for the reproduction of your high fidelity audio signal. That's the reason for having a sweep generator. Same thing with a television signal. A television picture signal is many megahertz wide, and by the way, that's AM on the old television. The only thing FM in a television set was the audio circuit. The picture circuit was an amplitude modulated signal with a very, very wide bandwidth of a few megahertz, about 3 megahertz. That's how they got the picture to come through. So all of the IFs in the audio chain and in the FM receiver chain had to be tuned to this wider peak. That's why you use a sweep generator. Okay, we'll get into more detail on that later when we actually start doing it. And for right now, I'm going to jump in, open this thing up, and we'll see what it looks like inside. My discovery, your discovery. This has been sitting here since I bought it, so let's see what's inside the box. First thing that was evident was somebody has been in here. There were 4 different types of screws holding this into the cabinet. That's never a good sign. The fact that all the screws are mismatched means this was taken apart, probably left open for an extended period of time, and they lost the screws. It's also evident that somebody has change one of these microphone type connectors for a BNC. Now that's not a bad thing. I'm going to be doing that to all of these because everybody uses BNC cables. Nobody uses these silly things. Even in their day they were unreliable, but it was what was available. The next thing I notice is it's got a newer line cord on it. Not necessarily a bad thing. It's putting a grounded plug on this is something I commonly do. But in the process of making it fit, they hacked the hole open on the cabinet to get this line cord to fit through. Somebody's actually chopped out a piece of this oval opening. The case itself isn't horribly bad. It's got a little bit of rust on the handle mounts and some rust showing through the paint. I guess that's rust. Maybe that's junk that spilled on it because something brown has been spilled on it over here as well. We'll see how this cleans up. I may or may not refinish this cabinet, but at any rate we'll probably remove the handle, glass bead the remainder of this poorly chromed finish off, and probably paint those black just so that they look a little bit better. But for now we'll set that aside. We don't need the cabinet on the bench. So let's see what we've got. Well, it's pretty dirty in here, and that's probably due to the fact that it was left open for so long. Somebody has scribbled or scratched the tube types into the chassis. And what? Oh, we have a bad vacuum tube. Let's see if you can spot it. Anybody see the bad tube? It should be pretty evident to anybody who's worked with tubes for a while. Let's put it up here and get some more light on it. There we go. Anybody spot the bad tube? This guy right here. Can you see the white showing through the tube shield? It means that tube has air in it. It means the gettering material, what is normally this silver black coating that's in here, this is designed to absorb any molecules of air or oxygen that happen to be left in after the manufacturing process, or that may bake out of the elements during use. When it turns white like that, that's a sure indication that the tube's either cracked or a seal has gone bad. So let's see if it's cracked. We'll gingerly move the, let's move this down like this. We'll gingerly remove the shield in case it's broken. We don't want to get cut. Oh yeah, it's got a crack right around here. I can see it clear as day. Now, will it come out in one piece? Let's see what happens. Ooh, I can see the crack opening up. Come on. See if we can work it out of there. I don't want it to shatter. Let's try grabbing it lower. Taking a chance on getting cut here. Ah, we got it in one piece. 6CB6. I should have a boatload of those. Oh yeah, that's really cracked. It goes directly across the center of the base between the pins, up around here and back down. Oh yeah, it's offset quite a bit too. I think the only thing that held it together was the internal structure of the wires inside the tube. 6CB6, so we'll have to put one of those in. Let's see if there's any evidence of anything else being messed with here. Looks like the RF section has all of its original screws. Hopefully that hasn't been messed with. A little bit of rust on the transformer. That shouldn't hurt anything. Oh yeah, somebody's been inside of this. There's a capacitor. I see this diode hanging in space here. So this filter cap, that diode, that's a new capacitor. It's a surplus cap or a pull from something that they've added wire to. Nothing wrong with that as long as it's done correctly. Back in the day, I used to do that a lot when I was young and poor. if you had, you know, a good pull from a defunct piece of equipment, you could replace the capacitor and extend the lead. So, you know, probably came out of something with a printed circuit board. That appears, yeah, the fresh solder joint. That capacitor is fairly recent, although it is a paper type cap. We in frame for that one? I think so. There we go. So that's a, oh, there's a tube down here underneath as well. That's interesting. Oh, that's got to be the oscillator then. Yeah, that's probably the oscillator tube. What's up above is probably just the variable capacitors. And they put the tube down here so that it can feed directly into the cavity or the enclosure for the oscillator. So we'll go through, we'll check and or replace these caps. I don't know what the vintage of those is. This may or may not. Yeah, I guess that solder joint's been worked too. So this is a change cap. 2 microfarad at 150. I'll change that out with a modern orange drop. That'll be, you know, this big compared to that. In fact, let me grab one up here out of the cabinet real quick. Oh, where did I stick it? There. Is that it? Nope, that's, there it is. Okay. Here's a 2 microfarad at 400 volts. That's a 2 microfarad at 150 volts. So you can see what modern caps are going to do for you. A much better cap and 3 times the working voltage. So we'll get all of this stuff changed out. 4700 picofarad. And we'll get all the caps changed, or the ones that need to be changed. Get a new 6 CB6 plugged in there and see what this thing does. Be back when the camera hit the off button on the camera. I went in here to poke around. I was going to change the connectors to BNC. Let's see if we can get this. See this resistor? Can you see what the lead's doing over there? Cold solder joint. It's just wrapped around the terminal and not even soldered to it. So I'm guessing whoever worked on this either added this resistor or had it out for some reason. Maybe, no, it looks like the original pot. Who knows? But that's not soldered. It's just hanging around the lead. So we have a little bit of work to do to this. Okay, we've been through the chassis. We've replaced the tube. All of the tubes that are in here tested perfectly. They tested new, with the exception, of course, of the broken one. And we had plenty of 6 CB6s laying around, so we found a good strong one and put it in there. I went ahead and marked the tube types and the calibration points. There's no tube layout in the manual for this. The schematic is there, of course. But I went through the schematic and verified that the correct tubes are in the correct socket. You never know when a piece of old gear like this, it hasn't been run for a while. And if it needs any calibration, I've got the calibration points marked now, because there was no indication of what was what on the chassis. And of course, when you're working on an unfamiliar, but easy for me to say, piece of equipment, it's nice to have markers as to what's what. And I also mark them on the bottom, so depending on where I've got to go to hook up a test lead and do a calibration, I'll have the pots marked. Even the oscillator tube here was in excellent condition. Lots of emission, no leakage. Went through and checked all of these capacitors, and it's obvious just from the fact that they're kludged together. They're obviously pulls from something. At least these two were. This is obviously a replacement cap. It was fresh solder joints, as was that. This appears to be an original. None of these leak, incredibly. Even with the hyper tester on the Heath kit over here, there was no indication of leakage whatsoever on any of these caps. So I've left them in place. That's fairly incredible. The electrolytics tested fine, this one and this one. Power factor is good, no excessive leakage, capacity is right where it should be. It's just mind-boggling. I am going to quote reform or check these. I hooked up these filter capacitors, the main rectifier filter capacitors, and on the Heath kit it blinked once and they went out. It charged right up and virtually charged instantly with no leakage showing. Now I haven't pulled any wiring off to check the capacitance. I can take a quick look with the scope after this thing's warmed up. However, since I do have our solar examiner here, I'll see what kind of leakage. I'm curious to see what kind of current leakage, measurable current, there is leaking through those filter caps, the main filter caps. Now again, the Heath kit showed nothing after our initial blink. So I'm not expecting to see much here, but we're going to find out. So I'm going to turn the voltage down. That's on 50 milliamperes. We're on leakage. And I'm just checking to see if it's safe to fire this thing up and see if it works. And nothing happened. Wow. So let's put this on 5 milliamperes. And there's nothing. Now you can, I hope the meter, is the meter in frame? No. Not quite. And there's an awful lot of light on it. Probably swamping it out. That better? That looks better. Okay, I'm going to, they're 450 volt caps, so let's bring the voltage up. Now it's showing a little bit of leakage at 250. And is it going to fall off? Or maybe I'm just seeing a leakage path to ground through a resistor. And let's see what the schematic tells me. I'll be right back. No, it's just the capacitors slowly reforming, and we've dropped down now to under 1 milliampere of leakage at 250 volts. And that's actually acceptable. In fact, it's not even a milliampere, it's 800 microamperes right at the moment. And still falling. So let's sneak it up some more. Let's bring it up to 400 volts. And that only went to 1.2 milliamperes. And it's falling. So I'm going to call those capacitors safe to power up at this point. Let's bring it to 425. 450. Right now we're at 450 working volts. And the current is still falling. It's slow, but it's going down. Now who knows how long it's been since this was powered up. Now there is one separate 450 volt section. Right now I'm testing two of them together through this resistor. There's another section that's separate, so I'm going to turn the voltage down so I don't pop the meter here. And we're going to hook this up to the other section of this capacitor. Can I get on that? Oh, not easily. Where's the wire go? Right here. Okay. And I'm seeing nothing to speak of. And it's falling, falling, falling. There's 200 volts and it's falling rapidly. 250 volts, it's under a milliampere. 3, still under a milliampere. There's 4, just going over a milliampere. There's 450 working volts. And it's hovering right around 1 milliampere. And slowly falling. That's incredible. So it appears that even the main filter capacitor in this is in good condition, or at least good enough condition to try this thing out. And it's coming down, coming down, coming down. So, incredible as it may sound, that filter cap is in excellent condition. Looking at this thing, the pilot lamp isn't blackened at all. All the tubes are in excellent shape except that one that had failed broken. This may not have any time on it to speak of. This may not have more than a couple of hours of usage on it. Now the capacitors again have been changed, so somebody went through this. The line cord's been changed and all the capacitors have been changed. And again, they are pulls, or at least a couple of them are pulls, but that's not a problem as long as they're good caps. Yeah, and that's fallen below 1 milliampere. I think this is going to be okay to power up, so I'm going to hook up a Variac and bring the thing up. Okay, we've moved up here to the actual 10-buck test bench, as you can see up here, and I felt it only fitting, since the manual says to use a VTVM and not a VOM in the notes, that I should use the ICO model 249 that was restored in one of the previous videos. And I just love that meter. I love the way it looks. It's not only a easy for me to say. It not only works very nicely and is very accurate now that I've netted in all the resistors. It's just a very pleasant piece to use. And I should have read all the notes earlier, because it would have saved me time trying to figure out which one of these pots was which one of them was the calibration pots and which ones were the front panel pots, because there's a note down here. All underlined switches and controls and connectors are on the front panel. So I could have instantly ignored the sweep width. I could have instantly ignored marker size, pattern size, because those are front panel switches, and then I just would have looked for the ones that aren't underlined and would have known immediately which three these were. Not that it took all that long to figure it out, but I should have read through the notes first. I'm always harping on you guys, read the notes, because voltages measured to ground with a vacuum tube voltmeter and a 4.5 megahertz crystal inserted in the crystal socket. And what's this guy right here? Now that's a 3.6 megahertz. That's close enough. All they want is something in the oscillator circuit, loading the oscillator so it's drawing some power. So that should work. I don't have a 4.5 megahertz crystal for it. It uses this style right here, and it would be nice to get a hold of some of these for 10.7 megahertz and 455 kilohertz to have the markers precisely set with a crystal, but there are marker inputs, external marker inputs, and we have a plethora of signal generators. Back there in the background we have that ICO. Over here we have another precision unit. This is one of the radios that's going to get restored. We have another sweep generator back here in the background, another precision sweep generator. So we have plenty of signal sources for markers, but it would be nice to have to plug in crystals. At any rate, let's move on. We have our Heathkit Variac up here, and the unit's plugged into it so we can bring the power up slowly and observe what the B plus is doing. So let's get on with it. Connect this to ground. That's set on DC volts, and it's been warming up for a few minutes, so it's nice and stable, and it's satisfying to see that the meter, even though I haven't touched this thing in a couple of months, is sitting dead on zero. We'll turn this on DC, and our first voltage point I want to take a look at is 330 volts right off the cathode, or pin 7 of the 6X4. So my eyes are going here. Bear with me while we get down in here. This is awful. Awful, awful, awful. I can't see anything anymore, and it's terrible. Absolutely horrible. The lighting and the acoustics up here are not nearly as good as they are downstairs. And I'm paying for it at the moment. Okay. We've got 1, 2, 3, 4, 5, 6, 7. Pin 7. Okay, we've got it. So we'll connect right here. That's bizarre. Oh, I know what's going on. Those capacitors have held a charge. I had begun to wonder, the leakage current was so low that I was beginning to wonder if they were merely open or almost open, so dried out that they weren't just weren't drawing current because of that. They seem to charge up so quickly. Typically when I have a very old capacitor and you hook it up to a leakage tester, it takes a long time for the current to fall off. If you remember that Zenith cap I had on the Solar the other night, it was taking a long time for the current to fall off, where these fell off almost instantly. This thing's still holding. We're on, it's not a lot of voltage. It's right now it's on 5 volts, but it's been 15-20 minutes since I was downstairs with this thing and it's still holding voltage. So we're going to put this up on the 500 volt range. And let's see, and that's another lesson. Start out on the high range when you're connecting to something, just in case that had been charged to 100 volts. Let's see here. We are looking for 330 volts coming out of there. So I'm going to turn this on. So the Variac is live. Where's the on for this guy? There it is. There's the on switch. And we're going to start bringing the voltage up. So we're up to 30 volts and about 100 milliamperes. And it's falling off because the filaments are warming up. Oh, and even the dial lamp is beginning to glow at the 30 volt level. So let's bring that up to 40 volts and 50 volts, and it's still only drawing under 100 milliamps. I'm not seeing any B plus yet, but the rectifier probably hasn't come up to temperature. Let's increase it to 60. Oh, there we go. Now we're starting to see some DC. So the rectifier filament, our cathode, is coming up to temperature. It's a 6x4, which means it's an indirectly heated cathode. Unlike a 5Y3 or a 5U4, where the filament itself is the cathode, this has an indirectly heated cathode. And we're looking at, let's see, we're on 500 volt scale, so we're looking at 150 volts DC at the moment. And we're only putting 60 volts AC in, so it looks like the power supply is coming up nicely. Let's bring this up, 70, 80, there's 80 volts AC in. Everything's looking good so far. Now we've come up to about 250 milliamperes and the tubes are starting to conduct, so you're going to expect it to start drawing a little more current. Probably should warm up the oscilloscope. It's been a while since I've played with this one too. Okay, there's power. Let that warm up. Let the CRT warm up. The rest of it's solid state. And that's 90. There's 100. 110. There's 115 volts, and we're at 300 volts. Oops, that didn't look good. Why did that drop all of a sudden? Taking the crystal out makes no difference. It's like something started drawing current all of a sudden. I'm going to turn this back down and move some stuff around here. I'm wondering about that shattered tube. Now I did some spot checks on resistors and everything looked okay, but it makes me wonder okay, I'm going to bring this back up to 115 volts. .300 volts on the B plus supply, and this is saying 330. So we're within 10%. I just want to make sure nothing starts glowing inside of that tube that was shattered. Everything looks good. We should have 160 volts on the other side of the resistor. Let's check that. And we have 150 volts, close enough. And 300 volts there. Everything's looking good voltage wise. Yeah, everything looks right. So, let me get the scope hooked up and we'll see what the DC bus looks like. There we have it. The upper trace is the DC ripple on 2 volts per division. So it's let's see, it'd be 500, about 200 millivolts, I guess, of ripple on the DC bus, B plus bus, which is pretty good. And the bottom one is the RF trace, the RF output trace, and you can see there's a spacing right here between these two blocks, and they're not actually where you see them. They're actually over further. It's the rolling shutter effect. It's the shutter of the camera speed is affecting the display or affecting the trace. But at any rate, you see there's a gap between those two. That's the blanking, so that when you're looking at this trace on an oscillograph, as they called it back then, and actually doing the alignment, you won't see the retrace of the scope. Of course, today that wouldn't be a problem, but on the earlier scopes, the unit provided the blanking. So it appears to be working. There's a little bit of on the top of the, well, you can't see it now because of the rolling shutter. This one you can see. You see it goes downhill a little bit. Looks like the AGC isn't working perfectly. I don't know what this thing looked like when it was new. It's certainly less than 3 dB. So it's probably fine. It's probably how it worked back in the day. We'll get this back downstairs. Now I was going to put all BNC jacks on the front of this thing. And let me zoom back out here. And I went looking. I have somewhere in the house, somewhere downstairs, I have a bag of like 30 of these BNC chassis mount jacks. And I can't find them. So I just ordered 40 more. That'll be here Wednesday, and I'll change these out and clean up the outer case a little bit. But I'd say this thing's up and working. I'm going to call this unit done. The capacitors that are in there are good enough. It'll work. I'm fairly confident for the amount of time I'm going to use it, it's going to be fine. And we'll move on to repairing one of the FM receivers so we can use this unit as well as try the other unit that's over here. And we'll use this oscilloscope and do an FM alignment like they did back in the day using one of these sweep generators. And it's going to be interesting. I'll put these on the bench and compare the functionality between that one And this one here, this one again has electronic sweep. The sweep's electronically generated. This guy over here, it's mechanically generated. And does that one? Yes, this unit actually has a blanking switch. Let's see, it's that one right there. That's the blanking switch on that unit. The other unit I have, I don't believe has a blanking switch. You had to live with the retrace on the screen. So that's it for this one. I'm going to box this thing up, call it done, and we'll move on to one of the FM receivers. Till next time, I'm the Radio Mechanic. Thanks for watching.